Okay, so imagine this for a moment. Humanity has always looked at the stars and wondered the same question. Could we ever reach them? The distances between stars are so vast that even our fastest spacecraft would take tens of thousands of years to arrive anywhere beyond our solar system. But physics doesn't completely close that door. Number 6. Generation ships. In 1929, British physicist J.D. Bernal introduced a radical idea in his book, The World, the Flesh, and the Devil. Instead of sending a small crew on a short mission, Bernal imagined an enormous artificial world drifting through space, large enough to support an entire civilization. The ship wouldn't simply carry astronauts, it would carry generations. The people who launched the journey would never see its destination. Their children, grandchildren, and distant descendants would continue living inside the vessel for thousands of years, until eventually one generation would finally arrive. One obvious destination is Proxima Centauri b, a potentially habitable planet orbiting the nearest star to our Sun, about 4.24 light-years away. At the fastest speed ever achieved by a spacecraft, around 70,000 kilometers per hour, reached by NASA's Parker Solar Probe, that journey would still take roughly 54,000 years. A generation ship doesn't solve that problem, it simply accepts it. From an engineering standpoint, the requirements are staggering. Completely closed ecosystems, recycling of air and water, agricultural systems capable of feeding thousands indefinitely, and life support machines designed to operate for centuries. But the most difficult problem may not be technological at all. It may be human. In 2014, geneticist Cameron Smith estimated that a generation ship would need at least 98 people to maintain enough genetic diversity for a long journey. Other models suggest much larger populations would be necessary. Yet genetics may be the easy part. Human societies have never existed in perfect isolation for hundreds of generations with a single unchanging goal. Every civilization we know has evolved through contact with others, trade, conflict, migration, and new ideas constantly reshaping culture. A generation ship removes all of that. What system of government could survive intact for 1,000 years? And what happens when Generation 400 decides they no longer care about the destination chosen by Generation 1? In the end, building the ship might be the easiest part. The real challenge would be building a society capable of surviving inside it. Number 5. Cryogenic suspended animation. There exists a microscopic organism called a tardigrade, sometimes called a water bear, that can survive conditions that would kill almost any other life form. When faced with extreme cold, radiation, or dehydration, the tardigrade enters a state called cryptobiosis. Its metabolism nearly stops. It dries into a lifeless shell and simply waits. Years later, sometimes decades, it can rehydrate and continue living as though nothing happened. That strange ability raises an obvious question. Could humans ever do something similar? The idea is often called a sleeper ship, a spacecraft where astronauts are placed into deep metabolic suspension during the journey. The advantage is clear. A sleeping human consumes far fewer resources, dramatically reducing the amount of food, water, and oxygen needed for long missions. In 2014, Dr. John Bradford of SpaceWorks Enterprises studied topor for missions to Mars. His analysis suggested lowering a crew's metabolic rate by around 75% could drastically reduce mission supplies. Applied to interstellar travel, the savings would be enormous. But biology is the obstacle. Scientists can already preserve certain cells and tissues through vitrification, preventing damaging ice crystals from forming. Human embryos and corneas are routinely frozen and revived. The human brain, however, is vastly more complex. It contains roughly 86 billion neurons connected by around 100 trillion synapses, forming the fragile structure where memory and identity reside. Freezing that structure without microscopic damage remains far beyond current technology. Medicine already uses mild hypothermia, cooling patients to around 32 or 33 degrees Celsius after cardiac arrest to slow brain damage during treatment. But the leap from hours of cooling to centuries of suspended life is enormous. Still, the barrier isn't impossible physics, it's unsolved biology. And that leaves an unsettling question. If someone sleeps for 100 years and wakes up again, is the person who wakes up truly the same individual who fell asleep? Number 4. Laser-Propelled light sails. On April 12, 2016, physicist and entrepreneur Yuri Milner stood beside Stephen Hawking and announced a project that sounded like science fiction. The project is called Breakthrough Starshot. Its goal is to send a spacecraft to another star system within a human lifetime. But the spacecraft wouldn't look like anything we normally imagine. Instead of a large probe, it would weigh only about 1 gram. A tiny microchip called a star chip would be attached to a thin reflective light sail only a few meters wide. A massive ground-based laser array generating roughly 100 gigawatts of power would fire at the sail, pushing it forward with the pressure of light itself. Within minutes, the probe could accelerate to 20% the speed of light. At that speed, it could reach the Alpha Centauri system about 4.37 light-years away in around 20 years. The technical obstacles are enormous. The laser array would need to span roughly 10 square kilometers. The probe would slam into interstellar dust particles at speeds where even microscopic grains would strike like bullets. And yet, if successful, the tiny craft could capture the first close images of another star system and transmit them back to Earth. Stephen Hawking died in 2018, 2 years after announcing the project. But Breakthrough Starshot continues, because even a 1-gram spacecraft reaching another star would prove something extraordinary. The distance between stars is not an unbreakable barrier, it's an engineering challenge. Number 3. The Alcubierre warp drive. In 1994, Mexican physicist Miguel Alcubierre published a paper that stunned the scientific world. Using Einstein's equations of general relativity, he showed that faster-than-light travel might be theoretically possible, but not by accelerating a ship beyond light speed. Instead, the idea was to move space itself. In the Alcubierre model, a spacecraft sits inside a bubble of distorted spacetime. Space contracts in front of the bubble and expands behind it, effectively carrying the ship forward. Inside the bubble, the craft never actually moves faster than light. The universe moves around it. The original calculation required an impossible amount of energy, equivalent to the mass of the planet Jupiter. Later research attempted to reduce that requirement. In 2012, NASA physicist Harold White suggested altering the shape of the warp bubble might dramatically lower the energy needed. The largest remaining problem is exotic matter, a theoretical substance with negative energy density required to stabilize the bubble. While it sounds fictional, a quantum phenomenon known as the Casimir effect demonstrates that negative energy densities can exist under certain conditions. In 2021, physicist Eric Lentz proposed a new theoretical model that might even avoid exotic matter entirely. No warp drive has been built, but the mathematics of general relativity does not forbid it. And in science, the difference between impossible and unimaginably difficult can change everything.
Number 2. Uploading human consciousness. In 2020, scientists mapped the complete neural wiring of a fruit fly brain, revealing about 25,000 neurons and 20 million synaptic connections. The project took years, yet a human brain contains 86 billion neurons and roughly 100 trillion connections. Mapping it completely would produce a dataset larger than the entire internet many times over. But if a brain could be mapped perfectly, something remarkable becomes possible. It could be copied, and data travels at the speed of light. A signal sent from Earth to Proxima Centauri would arrive in just 4.24 years. Instead of sending the human body across space, we might simply transmit the mind. Projects like the Human Connectome project are already mapping large-scale brain connections. But a deeper question remains unresolved. Philosopher David Chalmers called it the hard problem of consciousness. Even if we perfectly replicate every neuron and connection, would the digital mind actually be you, or just an identical copy? If your brain were scanned and transmitted to another planet while your body was destroyed, did you travel across space, or did you die, leaving a perfect replica to continue in your place? Number 1. Traversable wormholes. In 1935, Albert Einstein and Nathan Rosen discovered a strange feature hidden inside the equations of general relativity. Their calculations describing black holes suggested the existence of a bridge, a tunnel connecting distant regions of spacetime. They called it an Einstein-Rosen bridge. Inside such a structure, the distance between stars could shrink from light years to something closer to the width of a doorway. For decades, wormholes were treated as mathematical curiosities. But in 1988, physicist Kip Thorne showed that a stable, traversable wormhole might exist if it were held open by exotic matter with negative energy density. In 2013, physicists Juan Maldacena and Leonard Susskind proposed an even stranger possibility known as ER equals EPR. Their idea suggests that quantum entanglement and wormholes may actually be the same phenomenon viewed at different scales. In other words, entangled particles might already be connected by microscopic wormholes. Then, in 2022, researchers at Caltech using Google's Sycamore quantum computer simulated the behavior of a traversable wormhole in a quantum system. Information was sent through the simulated geometry and successfully emerged on the other side. Some physicists argue the experiment was simply quantum teleportation. Others believe the distinction may not be so clear. What we know for certain is this: the physics of wormholes does not belong to fantasy. It emerges directly from the two most successful theories humanity has ever created, general relativity and quantum mechanics. And so far, the universe has not told us they cannot exist. And remember, the universe doesn't reveal its secrets to those who rush. It reveals them to those who know how to look. Subscribe and keep listening to the silence.